Hi everyone. In this video, I am going to be deriving the gradient boosting algorithm for the mean square error loss. Hopefully, after this video, it's going to be more clear why we were talking about this algorithm. Hopefully, it will make sense. Okay. So, let's talk about some assumptions first. So the assumption kind of number one we have, so it's one of the assumptions of gradient boosting is that we are going to find a model that is a sum of some base models. And these models, TMs, are often trees. It's just boosting trees works very well. So a lot of the times when people are talking about gradient boosting, they are going to talk about boosting trees. So and always a gradient boosting model is going to be an ensemble of trees. But you can boost other models as well. So so that's kind of one assumption. So let's think about what an algorithm that is trying to minimize the mean square loss is trying to do. So we are trying to minimize, basically we have some training data with endpoints, and we are trying to minimize the target minus f on xi square. So that's what we're trying to minimize. And since we have some assumptions here, this is equal to basically to this. The sum of m equal 1 to capital M. Let me actually write this down here. So this is equal to minimizing 1 over n sum I equal 1 to n of yi minus sum tm of xi square here. So where we are talking about minimizing this, with respect to what are we minimizing? So we actually want to find M3s or M base models that will minimize all of this here. Okay, so this is with respect to T1 and T2, Tm. Okay, so it turns out that solving this problem exactly is very hard. So we're gonna have to make some other assumptions. Okay, so the assumption number 2 made by gradient boosting is that we're going to fit this model in a greedy fashion. So this is called a greedy algorithm. Okay, so what we're gonna do is that we're gonna fit first like a constant, okay, function. We're gonna do that. Then after that, we're gonna try to feed one tree. Once that tree is fit, we keep that, and then we're gonna try to feed another tree, and so on. So basically, and we are never gonna come back and change the previous trees. So all the trees we fit in the past, they are there, and we're just gonna find a new tree after that. Okay, so let's try to see how and this is called basically forward stage-wise fitting. And I'm telling you this because in some books you're gonna find these names, and they feel that they're too complicated for what they are. But so let's basically think about what would be like step 0 here. Step 0. So in the step 0, we're gonna find the function f0, which is gonna be constant. Okay. So our f in the step 0, our f of x is gonna be f0, basically, right? So what do we have here? So we have to minimize with respect to f0 1 over n sum over I equal 1 to n of yi minus f0 squared. Okay, so guys, what is the solution to that equation? Hopefully by now you know this because we have talked about this before, and otherwise I hope that you can prove that this is true. So the solution for this equation is f0 equal to the mean of the target variables. Okay, so basically that is f0. So now that we have f0, so let's talk about step 1. So in step 1, we want to minimize 1 over n sum of I equal 1 to n of yi minus f0 minus t1 of xi squared. Okay, and again the assumption is that the function that we have right now is f1 is equal to f0 plus t1, right? So we have f0, and now we want to minimize this with respect to all of the parameters of t1. So what are the parameters? Let's remind ourselves, what are the parameters of t1? Remember, t1 is a tree, right? And we talked about this before. This is maybe R2, maybe our problem is in R2, and R3 is going to split our data set in pieces. Here, and then here, and then like here, and then like there, right? So, and then each one of these joined pieces is gonna have a constant value for that tree. Okay, so the parameters of the tree are all of these, the splits, and then also the constant predictions for each of these joined regions. Okay, so but let's look at this more carefully, and and understand. So what is this? What do we call this? So if you remember, this is the residual after the step 0, right? So this is the residual for step 1. So we call this Ri. Okay, so really what we have here is that we are trying to minimize t1. We're trying to find t1 that minimizes this. And this is basically the regression tree that is trying to solve, basically is trying to fit this data set. So a data set in which we have like x and we have target Ri, the residual. Does it make sense? So basically the solution for this problem, for this stay watch greedy fitting that we are doing, is basically fitting the decision trees to the residuals, right? So let's actually look at step now basically remember, in step M, we consider f0, t1 and tm minus 1 are fixed, right? So we already kind of have f0, t1, tm minus 1, right? And we are trying to optimize the following. We're trying to minimize with respect to tm 1 over n sum of I equal 1 to m yi minus f0 minus t1 of xi minus, t2 of xi and so on, minus tm of xi square. And basically again all of this here until tm minus 1 is our current definition of our residual. So at step m we're trying to minimize with respect to tm 1 over n sum of I equal 1 to n of our residual ri minus tm xi square. And again, what we're trying to do here is basically to fit a tree with respect to this target, which is a residual. Okay, so let's kind of write down the algorithm in the way that the way we're seeing it here. So let's say gradient boosting for mean square error. Okay, so first of all, step 0, compute the best constant for this loss function, right, which is the mean of yi, our targets. Okay, and then we have for m equal 1 to capital M. First of all, we compute the residuals, which is yi minus fm minus 1 of xi. Okay, then we fit a regression tree tm using the dataset xi ri, right? Okay, then our new function is fm of x equal to fm minus 1 of x plus tm of x, and we finally return f capital M of x, which is equal to f0 plus the sum of all the trees. Okay, I hope that after, let me actually make sure this looks good. So I hope after this derivation you understand better where this algorithm comes from. Okay, see you in the next video.